This problem, number 50 on page 104 in Giancoli, is one of my all-time favorites. I affectionately call it the lawnmower problem. In this problem, we're looking at a person pushing on a lawnmower. We know the mass of the lawnmower, but what's key here is that this lawnmower is being pushed at a constant speed at first, which means that we're going to have to ignore the acceleration in the horizontal direction as we're looking at this lawnmower. First, let's draw a free body diagram of all the forces acting on the lawnmower. We're not going to draw any components of the forces at the moment. We'll just draw the forces themselves. Of course, the first thing that we want to put onto the diagram is the weight vector pointing downward. And we won't automatically put the normal force on because we're not sure about how strong that force is yet. We do know that the lawnmower is being pushed at a 45-degree angle and that it's experiencing some backward drag due to friction. And we know that upward there has to be a normal support force, and that's going to have to compensate for the weight vector and a component of the pushing force that's pointing in the downward direction. Note that if we put a set of Cartesian coordinates at the place of origin, then we can resolve the vector F pushing into two components. One that lays along the x-axis, which I'll be calling in future diagrams FP X to represent the push in the X direction, and one which is along the Y-axis. This is a perpendicular here and here, and of course that's going to be FPY. So what we're really dealing with is a free body diagram that looks like this, where we have two forces, not just one, representing the pushing force. And we could find out the length of those using the given information, and we'll be doing that in a moment. Meanwhile, though, we can create a net force equation in the horizontal direction and in the vertical direction. And that's going to help serve us in the case where the lawnmower is moving at constant velocity. So if V in the X direction is constant, that means the acceleration in the X direction is constant, or is zero, sorry, and the net force in that direction is therefore also zero. That indicates to us that these two forces, the friction force and the X direction component of the pushing force, must be equal. In other words, in the X direction, the net force is equal to everything contributing to forward motion, which would be FPX, minus everything resisting, which is our friction force. We'll use this equation a bit later as well. But for now, what this implies, if F net is zero, is that the friction force is equal to the X component of the pushing force. We're going to be using that and putting numbers in. In the Y direction, the situation is a tiny bit more complex. While we also know that the net force in the Y direction is zero, we have one force acting upward competing with two downward forces. So let's write that out. All forces pointing up minus all forces pointing down. The normal force minus FP in the Y direction plus the weight of the lawnmower. And if F net is zero, this implies, in this case, that the normal force is equal to the sum of the Y component of the pushing force and the downward weight vector. Let's work out the numeric details on the next slide. Okay, if that angle is 45 degrees, then the two components of the pushing force are going to be equal. Fpx equals Fpy. So using your trig, your SOHCAHTOA, the hypotenuse length, 88 newtons, times the cosine or the sine of 45 will give you that both of those forces are 62 newtons. We're going to use this first to figure out part B of the problem, which asks what is the friction force. Since the friction force is equal to the x component of the pushing force, that means that the friction force is 62 newtons to the left. You could say 62 newtons negative, or however you want to phrase that. Using the second equation, the one that related the normal force upward to the two downward forces, we have that the normal force equals Fp in the y direction plus the weight force, at least in magnitude, right? These are going in opposite directions. So since x and y components of that pushing force are equal, this is 62 newtons here, plus the weight force, which we can find by multiplying our 14 kilogram mower by the 9.8 meters per second squared gravitational acceleration. And that gives you about 199 newtons of force supporting the mower. Now here's where the problem gets really interesting and a lot more complicated in part D. What force must the person exert on the lawnmower to accelerate it from rest to 1.5 meters per second in 2 seconds, assuming the same friction force? What this problem is asking is for us to use the kinematic information to find the acceleration, the net acceleration of this lawnmower in the x direction, and then use that information to figure out what the new pushing force required will be. So first, let's write down our kinematic information given. We know that it begins at v0 of 0. We know that the final velocity we wish to achieve is 1.5 meters per second. And we know that the time that we wish to do this in is 2.5 seconds. That means that we can use the equation v, it doesn't look like a v, v equals v0 plus a t to figure out what the acceleration is. So algebraically manipulating that, a is equal to v minus v0 over t. You get the idea there. So that's 1.5 meters per second divided by 2.5 seconds, meaning that the net acceleration of the mower, the thing the mower is actually doing, is accelerating at 0.6 meters per second squared. We know from before that the net force on this mower is equal to the pushing force in the x direction minus the resistance from friction. If the friction force is going to remain the same as on the previous slide, and the net force is equal to m times this new a, why don't you calculate how strong the x component of the pushing force will be and check it on the next slide. I hope you did the calculations correctly. If you rearrange the net force equation on the prior slide, you find that the x pushing force, the x component of the pushing force, is equal to 70.4 newtons based on the fact that you are adding together the friction force and the net force. That means that the person has to push with a sideways force of 70.4 newtons to overcome the 62 newton friction and to accelerate that lawnmower. Now, that's not what the question actually asked. If you recall, it wanted to know what is the overall pushing force vector. So for that, we also need to consider the downward y component, because of course all we have at this point is this side of the vector. Okay, we are looking for not fpx, not fpy, but we want to have the hypotenuse vector fp. Assuming that the angle remains 45 degrees, then fpy and fpx must be equal, and we can figure out the length of fp. If we do not assume the same angle, it of course is a different story. If the angle remains 45 degrees for the pushing force, then fpy equals fpx. So if you use the Pythagorean theorem, you will find that the magnitude of the pushing force along that vector at a 45-degree angle is 99 newtons, new pushing force, no longer 88 newtons. Now, the one thing I wonder about this problem, though, is of course if you're a person pushing on a lawnmower or a vacuum cleaner and you want to accelerate it, probably you're going to not simply push more, but if you push on a shopping cart or one of those things, you push at a different angle, right? You make the angle different to make it accelerate. So I wonder, as we think about this problem, can you think of a way that you might figure out the new angle?